Hello everyone. This video is over item 5 in chapter 6 homework, which is pertinent to problem 6.49 in the textbook. And the question is about a car moving in a circular motion around a curve, a bank curve with an angle of 29 degrees. You are told that the road is slick, meaning the friction is almost zero, negligible. Yet the car stays in the road without any friction between its tires and the road, when its speed is 19 meters per second. Now, a similar question was addressed in the textbook. If you go to your electronic textbook, chapter 6, and you click on section 6.5, circular motion, this one here, if you scroll down here through section 6.5, after talking about centripetal force and centripetal acceleration, you'll see the question over bank road, which is similar to this question here. And you see the forces actually acting on the car. So let me go back here and take this image. What we are given here is the angle of the bank road, which is 29 degrees. And we are given the speed, v, to be 19 meters per second. And we are given that the friction is zero. The force of friction is zero. And we are asked to find the radius of this circular motion. So r is the unknown here. Now notice here when you apply the force diagram on this object, the only two forces acting on the object is the normal force, uppercase N here, and the weight, uppercase W here. If there is friction, there will be friction along the road here. It will be in this direction along the bank. This will be the direction of the friction, and it will be static friction because the friction will just keep the object in an orbit, in a circular motion. Okay, so that would be the direction of the static friction if there is friction. But since we don't have friction, so we can go ahead and remove this one here. Okay, so if we draw the force value diagram of the object, and that's the y and the x, and we are not interested in taking the x and the y along the incline, we are taking the horizontal x and the vertical y. So this is positive x, negative x, positive y, negative y. The forces acting on the object will be the normal force, and the normal force is forming an angle here. This angle is equal to the banking angle. This angle here is the same as this angle here. That's the banking angle. And we have the weight downward. Okay. There is no friction. If there is friction, it will be in that direction actually. If the friction is not zero, we'll have friction in this direction, and the angle here will be also equal to the banking angle. But here the static friction is negligible because the road is slick. So we'll remove the friction here. Now we know that there is a net force on the object causing it to move in a circular motion, and this force is in this direction. There is a net force that caused the object to move in a circular motion. And this net force is equal to what? This net force on the object is equal mv square over r, and it's lined up with the radius of the rotation. So it's across the x-axis here. That's the net force. So we know there is a net force F net in this direction. This is a net force. It's not one of the forces acting. It will be the sum of the forces acting on the object. So now if we go ahead and resolve the normal force into its x and y component, and we draw the force value diagram again here, positive x, positive y, and negative y. The x component of the net force here will be the normal force sine the angle, not cosine, sine the angle. Why? Because This will be x component of the net force, and it is opposite to the angle. So if you want to find it, you need to take sine the angle. Sine will be the opposite over the hypotenuse, and hence nx will be the normal force times sine the angle, while the y component will be adjacent to the angle. This will be the y component here of the normal force, the y component, and it's adjacent to the angle. So to find it, you have to take cosine the angle. Cosine the angle will be equal to the adjacent, which is n sub y, over the hypotenuse, which is the normal force. And when you solve for ny, it will be the normal force times cosine the angle. So here we'll draw the y component of the normal force, which will be n cosine the banking angle. Now the weight is already in the vertical direction, so it already has 90 degrees angle with the x-axis. So those are the three forces acting on the object in the x and y direction. And we know there is a net force in this direction. And this net force is equal to the centripetal force that will keep the object in a circular motion, which is this force here. So now we'll go ahead and apply Newton's law in the x and y direction in order to try to solve for the radius, and we'll see what we'll get. So in this type of problems, always go ahead and apply Newton's law in the x direction and in the y direction. Now in the x direction, we know that the sum of the forces is equal m times a, where a is special here. The a is the centripetal acceleration, because the object is accelerating in a circular motion. So the acceleration here is the centripetal acceleration. And we know that the centripetal acceleration is equal to what? Okay, recall the centripetal acceleration is v squared over r. So this means that the sum of the forces in the x direction is equal mv squared over r, where r is the radius of this circular motion. It's the one that we need to find. And now we'll go ahead and solve for the left-hand side and the right-hand side of that equation. Of course, the left-hand side, the sum of the force in the x direction. So we're taking the left-hand side here of Newton's law in the x direction. X direction, we have only n sine theta, as you see here from the force body diagram, n sine theta. This will be equal to the right-hand side of the equation, which is mv squared over r. So we get the left-hand side, which is n sine theta, equal to the right-hand side of the equation, which is mv squared over r. And let's call this equation equation 1. We applied Newton's second law in the x direction, and we got this equation. Now we need to apply Newton's second law in the y direction. Now in the y direction, the object, which is the car here, is not moving. There are no vertical motion. So the sum of the forces in the y direction is 0. And now we take the left-hand side. So that's the left-hand side of Newton's law. That is the sum of the forces in the y direction. And the forces in the y direction are 2. You have n cosine theta upward, and we have the weight downward. So it's n cosine theta minus the weight. This is equal to the right-hand side, which is 0. So this is equal to the right-hand side. Hence, now we have the equation n cosine theta minus w equal to 0. Now what does this equation tell us? It tells us that we can find the normal force in terms of the weight and cosine the angle. So normal force is simply the weight of the object over cosine the angle. If you are not familiar with the math, we add w to both sides of the equation. This will cancel minus w on the left-hand side. Then we divide both sides of the equation by cosine the angle. So we'll get this equation. Let's call this equation number 2. So you can see here from equation number 2, a formula for normal force, which we can plug it into equation number 1. So plug the normal force formula in equation 2 into equation 1. And if we do that, we replace n by w over cosine the angle. So now equation 1 will become w over cosine the angle. This is times sine the angle equal to mv squared over r. I'll go ahead and complete the problem on this side here. So I'm going to create a line here to separate those two sides. After we and I'm going to use a green font here. Notice here that we have sine over cosine, which will give us tangent. Also, we can replace W, which is the weight, by its formula, which is mg. So if we do that here, we'll have on the left-hand side, so again, this is equation 2, the left-hand side of equation 2, it will be mg, which is W, and sine over cosine is basically tangent, the angle. This is equal to mv squared over the radius of the rotation r. Now m here can be cancelled out. M is not given in the question, so this is good news. We can cancel out m. So m is cancelled with n. And now we can solve for r. To solve for r, you multiply both sides of the equation by r. This will cancel r on the right-hand side, and it will place it on the left-hand side. And then we multiply both sides of the equation by 1 over g tangent theta. So this will cancel g tangent theta on the left-hand side, and it will place it on the right-hand side. And now I'll start here with the right-hand side, which is r equal to v squared over g tangent the angle. And now we can plug the values. Now the values, of course, will change from one question to another. Remember, the questions in mastering will vary the values. But basically, you'll have the value of the velocity, whatever it is, and it is squared, over the value of g, which is 9.8 meter per second squared, times tangent the angle. Now, very important here when you do the calculation on the calculator is to switch the mode from radians to degrees. Very important, don't forget that. So you carry out the calculation and the answer will be in meter. Why? Because meter square here, you have meter square over second square in the numerator, and you have meter over second square. So basically you have meter square over second square in the numerator, divided by meter over second square, which means you are multiplying by second square over meter. Second square will cancel out with second square, and the square here will cancel with the meter, and you get the answer in meter. Alright, so hopefully you found this video educational. Let me know if you have questions. Thank you.